All right, so I guess we'll wait a few minutes for everyone to show up. So here's what we have to do today. We have two problem sets from chapter 4, and then we're going to go through chapter 5, which is not extremely long. This is our discussion about trigonometry. Now, we have to hustle a little bit here because if you look at the calendar, let's see, let's get the old calendar out. Ideally, we'd like to get our second midterm done before Thanksgiving. Now, Thanksgiving is a little early this year. It's the 24th. Oh, God, I hate it when the calendar starts on Monday. I'm so not used to it. Let me try another one. Let's find a normal one. Here we go. All right, so let's try that again. So today's the 2nd. The 23rd is the day before Thanksgiving. We're not going to have class on the 23rd. So that means if we want to have our test before Thanksgiving, we have to get it out of the way on the 16th. So that means that today we have to finish these two problem sets and chapter 5 so that on the 9th we can do the chapter 5 problem set and also the sample midterm. Now we should be able to do that, but we don't have any time to waste either. All right, so that's what I'm mentioning, why I'm mentioning this now, so that on the 16th, we can have midterm number 2. And then when we get back, even then, we've got the 30th. And let's get a December calendar out of here. In December, then, so we'll get back, oh, for God's sake. This is so annoying. The 30th will be back, and the 7th. All right, here we go. So let's try that again. So when we get back from Thanksgiving, we'll have class on the 30th and the 7th. Now, I think the 14th is when we're supposed to have our final exam. So that means we'll have 2 weeks when we get back, which means we have to cover the new material and we have to review. Okay, so it's getting a little tight, but we can do it. All right, so in the meantime, what I'd like to do is get started today with the chapter 4 problem sets. Now, I'm going to be working on these. As you can see, I'll be writing on the screen here. I do have a tablet, as it turns out, right on the screen, which is very convenient. And so what's good about doing this online today, sorry, is that we can save these. And I will post a copy of these solutions online along with the recording that we're making today, because this class is being recorded. So that way you'll have a copy of the recording as well as these solutions. So that way you'll have all the information you need. All right, so let's see, where are we? Let's do number 1. All right, so we'll start here. Now, these questions are kind of broken up into pieces. Here we're looking at exponential functions. We're looking at finance. We're looking at growth rates. In the second part, we're looking at exclusively exponential and logarithmic functions. Okay, so that's what we'll be covering here. And then we'll get, when we're done with 5. Now, if we have a little time at the end, maybe we can start to take a look at the next chapter, which is 11, but I don't know. We'll see how that goes. All right, so let's see what we can do with these. All right, so let's get back to number 1. Here we go. Here we go. All right. So with these, what we're trying to do is identify the formula, or sorry, the actual equation for an exponential function that passes through those 2 points. Now, we've done this many times with straight lines. All you need to uniquely identify any straight line is 2 points. We can use them to calculate the slope and then the intercept. Now here, the process is a little different, but same principle. You only need, because there's only 2 variables in our exponential function, remember it's written like this. There's only two unknowns here, or two variables. So therefore, we only need 2 points in order to uniquely identify this equation. The only problem is it's not a linear function. So that means it'll not be as straightforward. What we have to do is some substitution, as you'll see in a second. So what you're going to do is start with the first point. And of course, this is X and this is Y. So this equation can be rewritten as Y equals A B to the X. So what I'm going to do with point 1 comma 6 is replace the 6 of the Y with a 6 and the X with a 1. And so what this tells me is that 6 equals A times B. And now what I can do is solve for either variable by itself. Okay, so let's say that I decide to write this as 6 over B equals A. Now that by itself doesn't tell us anything, but what it does let me do is take the second point, which is 3 comma 750, and then write it like this. Okay, and now what I can do, because I already know that A is equal to 6 over B, this is where the substitution comes into play. Oops, let me fix that. 6 over B times B cubed, which means it's 750 equals 6 over, this actually simplifies to 6B squared, okay? Because you've got B cubed divided by B. And so that means that I've got 750 over 6 is B squared. Well, 750 over 6 is actually 125. So that tells me in turn that radical 125 is B. Now, this one we can simplify. We've done this before. You can rewrite this as 25 times 5. And let's do this. And so this is my value for B. And now this can be substituted back over here to solve for A. Now, we know that traditionally we do not want to have, if we can avoid it, a radical in the denominator. So here's what we're going to do. Let's rewrite this. We're going to rationalize the denominator. So what do we end up with after all that? Okay. So now this is as simple as they're going to get. So the equation itself that we're actually looking for can be written in the following way. So we have our solution for A and B. And since Y equals B to the X, the equation that we have just identified is 6 radical 5 over 25 times 5 radical 5 raised to the X power. That's it. And that is the actual final answer. That's the equation that contains 3 points. And it is, as you can see, an exponential function. And so you can imagine if you drew a picture of it, it would end up looking something like this. It grows very, very quickly after it reaches a certain point. Now, all of these are exactly the same. The only thing that changes is the actual numbers. Okay, so our procedure will be the same for all of them. All right, so we're going to do that for the next one. Now, by the way, you can always double check this by plugging the points into it and making sure that they work, but we don't need to do that right now. But you can do that. Like, in other words, you could say, listen, is it true that 0.1 comma 6 actually fits in this equation? And you could replace the 6 with the y with a 6, the x with a 1, and you see that it does work correctly. All right, so let's take this one. So this implies that 2000 equals AB to the 1. All right, well, that's easy. So again, what I'll do is I'll just rewrite this. I could do either one, but I'll just rewrite this as 2000 over B equals A. I have a chat. Oh, it's okay. It's okay if, yeah, I mean, this is the only time we've ever done a Zoom, so you might not be familiar with how it works. It used to be like 2 years ago during the COVID, all the classes were done like this. So it was a common thing, but now it's been a while. But it's good to know that this technology exists, that like on a day like this, I don't have to like completely cancel the class. I can still do this, even though I shouldn't be in the room with you. I can still do the class. And so this way we don't miss any time. But anyway, oh, here we go. Yes, the second one. So this time 20 equals A B squared. And now once again, we'll replace the A with this result. And this simplifies to 2000B. And then we can have 20 over 2000. And that reduces to, it's actually 1 over 100, or we can either write it as 1 over 100 or 0.01. And now that can be substituted back over here. And so we'll have 2000 over 0.01. And that actually works out to be 200,000. So the final result, the equation that we're actually identifying, is 200,000 0.01 to the x. So it's actually declining. Oh, what did I do? It's actually decreasing because the growth rate is less than 1, or the growth rate is B plus 1. So that means if you drew this one, you would see that it's falling off, something like this. All right, now it doesn't ask you for that, but it's just in case. All right, so there's 2 more. Now some of these, the answers will be fairly nice, and some of these, they'll be horribly messy. You know, that's to be expected with exponential functions. All right, so we make our substitutions. And so now if we multiply both sides by B squared, I'll end up with this result. All right, now over here, I have So that means that 1 equals a b cubed. And of course, a is defined as 6b squared, or 1 equals 6b to the 5th. And so that means that 1/6 is b to the 5th. And now in order to solve for that, what I have to do is take the 1/5 root of both sides of the equation. And so on the right-hand side, that just leaves me with b. So that's my final answer for, you can see what a mess that is. So we'll bring that over here. Wow, now that this is a very, very unpleasant answer, isn't it? But that's what it is. I mean, the answer, it is what it is. We can't always expect to get integers. Now, if we needed to, I mean, we could sit down and take a calculator and figure out the exact numerical value of these. But it's not really necessary. We can just leave it the way it is. So that means that finally, when we're done, we have 6. Wow. God, mess. But that's the answer. I mean, that is the function that we just estimated or identified from this information. Ooh, okay, I think the next one will work out a little more easily. I don't think it's quite as ugly as this one. So let's see how that goes. Yeah, it's a little bit simpler. So this means that 1 equals ab to the 3rd, or whatever a cubed, b cubed is a. Over here, we have 5/4. Y equals ab to the x. 4 therefore equals a b to the 5th. Let's make a replacement or substitution. Okay, so yeah, this is looking a little simpler because what we actually have here is 4 equals b to the 5th over b cubed, which is the same thing as saying that 4 equals b squared, 2 is b. Right, and that means that 1 over 2 cubed is a, 1/8 is a. Okay, and therefore the final answer is yeah, now that's a lot nicer. I think you'll agree. That is this equation that we just identified. Okay, now I'm just going to do one thing here. This really drives me crazy with Microsoft Word. They do not assume that you want page numbers unless you tell them otherwise. I think that's absolutely ridiculous. With such a long, this document, by the way, by the time we're done, it's going to be quite long. And so that's why I think you've got to have page numbers. Okay, I just can't deal with it when it's not. No page numbers really annoys me. So there they are. Now these are the finance ones. So the formula that we're actually focusing on here is this one. Okay. Anyway, so let's take a look at this first one. Now the formulas that we'll be using here. A equals P 1 plus R over N to the NT. This is the future value of a sum. Okay. So you recall that A is the future value. P is the principal. That's the amount you started out with. R is the rate of interest. N is the compounding frequency. And T is time. Okay, so all you have to do is plug in these numbers to come up with, let's say, this one. Let me move it down here so you don't have to scroll back and forth. Jesus Christ. Okay. Yeah, it's just unbelievable. Sometimes it just has a mind of its own. Word, I mean. All right, so what do we know? So we deposit 10,250 in the bank. That's our principal. 10 years. The rate is 4. Sorry. Compounded quarterly means n equals 4 times a year. All right. What's the future value? All right. Well, literally, that's all you have to do is plug in those numbers. All right. So what you should probably do to get this out of your calculator is first simplify. So 0.04 over 4 is 0.01. 4 times 10 is obviously 40. And so then when you multiply that out, what you should get, rounded to dollars and cents, that is 15,000. 260.85. Okay, and that's it. That's all you have to do. Now, for 6, they want you to change the assumption of compounding frequency to monthly. In other words, n is 12 now instead of 4. So you're going to have A equals 10,250. 1 plus 0.04 over 12. And then you have 12 times 10 instead of 4 times 10. So this one has to be rounded a little bit. This is 0.04 over 12. But when you multiply that out, you should get approximately 15,000. 281.03. All right, so you notice how it goes up a little bit. Every time we increase the compounding frequency, the future value has to go up. I'll just make a note of that here. The future value increases because compound interest increases. Okay, whoops. All right, and that's the reason. The simple interest is not changing. It is not affected by the compounding frequency, but the compound interest is. Now here, they're having us change it again, except this time, we're going back to quarterly compounding, but we're changing the time frame to 20 years. Okay, so let's see if I can steal this and recycle it. So what we need to do is change 2 things. So the compounding frequency is back to 4, but now all of a sudden it's a 20-year investment instead of 10. All right, so let's see how that affects our results. We should expect to see it go up because the money's being left in the account for more years. So it's 1.01 again, but now the exponent is 80. And that's going to give us about 22,721.33. So just as we predicted, it's more than it was for 10 years. In fact, it's quite a bit more. Right. Okay, now. All right, I had lost my place. 5. This was 5. This is 6. And this is 7. Okay, great. Now 8, it's a similar problem, except this time the compounding frequency is semi-annual. It's actually a completely different problem. These two were both based on problem 5. So this one we're starting all over again. So we'll grab the formula. Yeah, sometimes, there we go. Sometimes it'll let you copy and sometimes it's just not so easy. All right. So this time, what do we know? The deposit is 6,500. The rate is 3.6%. The compounding is semi-annually. The bank is 20 years. We leave it there for 20 years. So let's plug in the numbers and let's see what we get. Oops. All right. I rewrite these. I have to be careful with this tablet, with the spacing. All right, that's better. All right, let's try that. Okay, so again, it's 6,500, 20 years, but it's semi-annual compounding. So we actually end up with 1 plus 1.8% or 1.018 is raised to the 40th power. And so now we're going to wind up with 13,268.58. Okay. Now this next batch is pretty straightforward because we're just evaluating these functions at a particular value of x. So it's not very hard. In fact, we've done the most difficult one is finished. The ones at the top, I think, where we had to find exponential equation, I think those are definitely the most challenging in this problem set. The rest of these are actually very down to earth. So like this one, for example, f of -3 would mean you simply replace all the x's with a -3. Okay, so here we have 2. Now 5 to the -3rd power is the same thing as 1 over 5 cubed, which is 2 over 125. Okay, and that's it. That's all you had to do. It was so simple. Wow, these are nice. We like these. Now this one, -4 to the 2 times -1 plus 3 power. So we're going to have -4 now. -2 plus 3 is 1. And that just means, that just leaves us with -4. Huh. Well, that was easy. Now for this one, wow, this one couldn't be any easier because f of 3 simply equals e to the 3. And you're done. That's it. E to the 3 is a constant. There's no need to do anything with it. I mean, if you want, you could calculate the exact value of it. You could go right to your calculator and take care of it, but it's going to be 20 point something, I believe. But yeah, we can just leave it like this. Okay. And then there's just this one more, and then we can do some growth problems. All right. So f of -1 would mean minus 2e to the -1 minus 1. Yeah, that's it. Wow, that was so easy. Okay, now these growth problems. Now, these are all exponential problems, but we use slightly different notation. So instead of writing our equation like this, we write it like this, where n of t is the number or value at time t. So it's an exponential function because t is in the exponent. Now here, telling us that the growth rate is 9%. Now, b is 1 plus the growth rate. So therefore, this is 1.09, 1 plus 9%. A is the initial value. Which could be thought of as n of 0. Now, here they're telling us that in the first year, 2012, this is what we mean by the initial starting point. So n of 0 is 23,900 because we have that many foxes in the year 2012. So 2020 is what we're interested in. This is year 8. That's what we're trying to solve for. So what we're going to do is write the equation using the information that we have. So we know that A is 23,900 and B is 1.09. So now in order to solve for n of 8, oh, that's okay. Sorry, I was hoping that everybody would see the message. I guess not you can't assume that everybody looks at their emails all the time, but we're all set now. And by the way, this is being recorded so that if you missed anything, you can just watch the recording. Oh, by the way, I forgot to mention this in the beginning of the session. Even though the session is being recorded, it's going to be a very large file, the tape. So what I know from experience that Moodle is not really able to store large files like that. So what I will be doing instead is that I will be posting it on my YouTube account, which I'll show you right now. And I will be creating a separate playlist for it. What you have to do, as far as I know, in order to get at my website, you just need to search for my name, apparently. So you can see it's a little a. And when you go to my channel, you can see there's a bunch of videos left over from past semesters, especially during the COVID. And then it's not there now, but we'll have a separate playlist just for this class. And that way you can find the video very quickly and easily. So I've got other classes. In fact, this one you see here, I should have labeled it a little differently. I have the same class on Mondays and Thursdays. That's what this one is. For ours, I'll make sure it's labeled properly. It'll say math 1150 Wednesday or something like that, so you know which one it is. All right. So, theirs is similar to ours, but theirs is only like half the length of our class. So if you watch that one, you might miss something. So when it's done, now this will probably not be ready until this afternoon or tonight because the video has to be processed. It has to be converted into MP4, which is standard YouTube formatting. But once it's done, you can watch it as many times as you want. And you can skip through it. You can just find the parts that you missed. So that's one of the nice things about doing this online is that you've got a copy of it. And also the document that I'm working on right now, I will be able to save it and post it on Moodle as well, just in case you miss something. All right, well, anyway, so Innovate would just be solved by substituting 8 for t. And so when you do the math, you grind out those numbers, you'll see that that's going to be about 47,622.25. Now, because these are foxes, it has to be an integer, so we're going to round it to 47,622. Okay, we can't have a fractional number of foxes, can we? No. All right, so that's how that one works. And now this one is a house. The house is valued, so 1985 is our starting point. Oh, you're okay, your email. I see. Okay. Yeah, the thing is you really cannot completely depend on any form of technology. I mean, yeah, everything is supposed to work beautifully, but it's been my experience, especially emails. You cannot assume that any email that you've sent is actually going to get where it's supposed to go. You should never, ever assume that. Just double check, do whatever you have to do to make sure that it gets there, because if you don't, you're going to have trouble. It happens all the time that emails simply do not get delivered where they're supposed to, or else there's just the Wi-Fi is acting up. I think that by now they would have figured out how to make the Wi-Fi more reliable, but it just hasn't happened. Like right now, my phone, where I live, I can't make phone calls with my cell phone. The reception is so awful. I have to use a landline. It's useless in the apartment and the grounds outside here too. And in fact, if I'm walking around outside trying to pick up my mail, I can't, the emails don't even work. So I can't even see if I have a package or not. But anyway, enough of that. So t equals 0 in 1985. And so n of 0, the starting point is 110,000. In 2005, which we'll define as year 20, we have 145,000. What's the growth rate? Okay, so remember, the function looks like this. This is A right here. Starting value is A. Now, we also know that in year 20, the house will be worth 145,000. So what we can do here is write 145,000 equals 110,000 times b to the 20th power. And by doing so, we can solve for b. So we divide out both sides by that 110,000. And then we can take the 1/20th power of both sides. So what that means then is that when you calculate 145,000 over 110,000. That's approximately equal to 1.0139 equals B. Now remember, they're asking for the growth rate. So since B equals 1 plus the growth rate, that means that 1.0139 equals 1 plus the growth rate. And therefore 0.0139 is the growth rate. And that, of course, is the same thing as 1.39% per year. So the value of the house over this period went up an average of 1.39% per year. That's what this is telling us. Now, in part 15, we're being asked to do something related to 14. What is the predicted house value in 2010? Okay, so we have B and A. All right, so that means the equation. We already knew that A was 110,000. B is 1.0139. So that's the full equation now. We have both A and B. So now the year 2010 in this example would be year 25. Okay, because the starting point was 1985. So for T equals 25, so therefore the answer is and that turns out to be 155, 335, 52. And that's our final answer. Okay. So now, in this example, we have 2007, the car's worth $38,000. 2013, 6 years later, the value is 11,000. Of course, it's a car. The value declines over time. We're going to try to figure out what is it worth in year 10. All right. So what that means then is that we need, first of all, this is A. So we have to solve for B, just like we did up here, and then use that information to come up with our prediction. So we know that in year 6, the value is down to 11,000. Okay, so we're going to take the 6th root of both sides. And let's see. So this on the left-hand side, we have 0.8133, and the right-hand side would be. So our equation becomes so remember A is 38,000. B is 0.8133. And so our job is to figure out n of 10. What will the car be worth in 2017? All right, and that's 4811, rounded to dollars and cents, 62. And of course, it's worth less than it was in the previous years because of what's called depreciation. Okay, the growth rate of the car is negative. The value is shrinking over time. Okay. Well, all right then. That one's done. So now we can move on to part 2, where we look at our exponential and our logarithmic functions. So these are very different types of problems than the ones we've just been working on. Here, we're trying to focus our attention on the properties of logarithms and exponential functions. So let's see. First things first, let's just make some space here. Log, now here we've got constants. I mean, these are not obviously real numbers, but no matter what's going on here, this is the same thing as saying 4 to the m power equals q. So you're basically taking the base and raising it to this power to come up with this result. And so similarly, based on that logic, in the second case, we must have a to the c power equals b. In the third case, we must have 16 to the x equals y. And in the last case, we have x to the y equals 64. So in other words, when it says exponential form, it just means you need to write it out in such a way that there's an exponent involved. All right, now for these, we're going the opposite direction. We're working it backwards. We're starting with an exponential function and turning it into a log. So how does that work? Well, for this first one, we're being told that log base 4 of y equals x. Okay, so based on that logic, this next one should be log 10 of b equals a. And if you forget, just keep in mind the function log is designed to return an exponent. Okay, so the exponent has to be on the right-hand side of this equation. So this one is telling us that the log of log base e h equals k, but this one can be rewritten as natural log h equals k. Okay. And then finally down here we have log 19 of y equals x. And that's it. Now we're going to solve for them. We're looking for actual numerical values. Okay, now how are we going to do that? Well, it's a two-step process. We write out the equivalent exponential expression. Here, for example, this tells me that 3 squared equals x. Because it's a log, it's written as log base 3 of x equals 2, but this is equivalent to saying that 3x equals 3 squared equals x, which implies that 9 equals x. Okay. So they're all going to be the same. Rewrite it as an exponential function, and then you can solve for x. So this one tells me that 2 to the minus third is x, which is 1 over 2 cubed. 1 over 8 is x. Okay. Now here, this one is the same as saying 5 squared is x. So it's just 5 to the second power equals x. And then finally down here, this one is equivalent to saying that 3 cubed is x, or 27 is x. All right, now we're going to simplify. Now, the properties that we will be using here are these. Just a quick reminder, no matter what the base is, the log of a product is the sum of the logs. The log of a ratio is the difference and then finally the log of an exponent is n times the log of x, right? Okay, so these are the properties that we will be using to simplify these expressions. Now, the important thing is that this only works if all the logs have the same base. So here, for example, this is just going to be log 2x to the 4th times 3x to the 5th, or 6x to the 9th. Now, if you wanted to, this one could also be rewritten as 9 log 6x. They both mean the same thing based on that last property. Okay. Now, this one is a ratio because you've got the log of a difference. And now you can simplify it to log 2x to the 7th, or if you choose, you can rewrite it as 7 log 2x. Right. How about this one? Now, for something like this, there's a few ways you could go about this, but it turns out you can simply rewrite it as 2 times 3 times log x times x plus 1. So you've got 6 log x squared plus x. And then you could just leave it like that. Now, this last one, we're actually combining a couple of different properties. They all have the same base, so this can be rewritten as log. So the two that are being added with x and z, the one that's being subtracted actually, here's what we're going to do. Before we go any further, just to keep it simple, let's rewrite this. You could actually, you know what you could do? Let's do this. It really doesn't matter. In fact, I'll tell you what, let's just do it directly in the first place. If we're going to change this one, let's change this one too. Let's write it as plus log z cubed. I think it'll make it easier for what's coming next. And then we'll have log x z cubed all divided by y to the 1/2 power. And that's good enough. That's fine. Okay, so those are just simplifications using the properties of the logarithms. Now, these, though, you're actually solving for something. Now, here's what we're trying to get at. In a case like this, just remember, I'm going to write down some properties that you should remember. The log for any base of 1 is 0. The log of any base, let's say a, of a to the x is x. So here's what we're going to do. Look at this and say, well, what's going on here? We don't have a common log or a common base on either side. So our best bet is to do this. We're allowed to take log 9 of both sides. We're allowed to do any operation to both sides of an equation as long as it's the same on both sides. And so that reduces to, on the left-hand side, based on this property, x minus 10. And on the right-hand side, that just reduces to 0. So we just end up with x equals 10. So the strategy was to, simplify, turn this into a simpler equation by applying logs to both sides. Now, this next one is very similar, except it involves natural logs. So with these, I think our strategy should be to do this. Rewrite this as e to the 6x equals 13 halves. Then take the natural log of both sides, because log is the same thing as log base e, and the natural log of e to the x is just x, which implies that log e to the 6x is just 6x. So therefore we have 6x is log 13 halves, or very simply, and that's it. Okay. Now, here, this one, we'll clean it up a little first. We'll add 8 to both sides. So if I add 8, that reduces this to minus 54. I'll divide out the negative 5. So I'll have e to the 9x minus 8. And then I'm going to employ a strategy like the one I had before. I'll take the natural log of both sides. And so that reduces to 9x minus 8. Okay, now the rest is just normal algebra. Okay, and we're done. All right, let's see. What do we have here? Now, same thing. You should probably always simplify as much as possible before you apply any of these rules. It'll be easier that way. It reduces the risk of mistakes, which is, of course, what we want. And then we'll apply the log to both sides, natural log, that is. If I apply a different log, it won't help. Eight x plus 3 is ln 3/5. So now, again, just apply a little algebra. And then we divide by 8. That's it. All right, and then one more. So let's see. Let's simplify. Add the 7, divide by the 4. And then take the logs. Okay, and that's really as simple as it's going to get. Now for these, we're going to do something similar. We start out with a logarithmic expression. We're going to try to rearrange it into an exponential expression and then solve for x. Like here, first let's divide out that 5. And now this is easy because this is telling me that 7 squared equals x. All right, because these two expressions mean the same thing. That's the key to the whole thing right there. Now for this one, let's see. Oh, I'm checking to see if there's any chats that I missed. No. Okay, good. Divide out both sides by that -8. And again, we're using the properties of logs. This tells me that 9 to the minus second power is x, which means 1/9 squared. Or in turn, that simply means 1/81. Okay, now what about this one? Subtract both from both sides, the 4. And now this one tells me that 2 squared, actually the -2, I should say, is 9x. Okay, because these two mean the same thing. So this is 1/2 squared. And That means that 1/4 is 9x. So if I divide both sides by 9, there you go. And okay, one more. Wait a minute. So first, let's get rid of the 6 here. 2 log 2. 8x plus 4 equals 4. Divide out by 2. And that is the same thing as saying that 2 squared is 8x plus 4 because of the properties of logarithms. 4 is 8x plus 4. 0 equals 8x. And that means that 0 is x. Okay. Okay, now these are a little different because what's happening is that we're leaning on the so-called one-to-one property. Which simply means that if you have the same base, log b of s equals log b of t, implies that s must equal t. So that means when you see these both are natural logs, I can just rewrite it as 10 minus 3x equals minus 4x. Add 3x to both sides. And that means that negative 10 is x. Okay. Same thing here. On both sides, we have the same base, log e. So now I need to do a little rearranging. And then I can rewrite that as 3x equals x squared. Divide out the x from both sides. And there we go. Now this one, we're going to just use the properties of logs. This one is the same thing as saying 2 cubed is 7x plus 6, 8, 7x plus 6. 2 is 7x. 2/7 is x. Okay. And then finally, we have this one. 6 minus x equals 3x. 6 equals 4x. 6/4 equals x. 3/2 equals x. Okay. All right, and that'll do it. We are done with this, at least. All right, so I'm going to save this. Now I'll be posting both of these onto Blackboard. So you'll have all the handwritten solutions. Meantime, we can get back to 5. Now, I think we started to go over this the last time. We started to briefly review the trig functions. So let's just look at that real fast again. Hold on one second. Today is the 2nd. So just a quick review. We have the angle, these are all defined on angles, okay? All trig functions are defined with respect to angles. So imagine yourself having a triangle like this. It's a poorly drawn right triangle. Here's the angle. This is the adjacent side. It's right next to it. This is the opposite side. And then this is the hypotenuse. Okay, so the sine is the opposite over the hypotenuse. So if we had numbers, we could calculate it. We don't need that right here. We just want to define these. Okay, now we had three others, which are inverses of these. The cotangent is the inverse of the tangent. The cosecant is actually the inverse of the sine. So already here. And then the secant is the inverse of the cosine. And so those are our 6 basic trig functions. Okay. So I'm pretty sure we started to review this last time. Now, the next thing we want to do is formally define what we mean by an angle. So we start by connecting two rays, as they're called. A ray is basically a line with a physical starting point. So a line, as you know, goes on forever up to positive and negative infinity, but a ray has a very specific starting point. So those arrows are meant to tell us that these are both rays, but while they start here, they go on forever. The angle basically is trying to tell us relative to a circle, which is obviously all the way around the entire XY coordinate system. The angle tells me how far is this angle apart, how far are they apart relative to this entire circle. Okay, so 1 degree is 1/360th of the rotation of a circle. Okay, so it's basically telling me what fraction of the circle am I covering when I go from this point, which is the starting point. In fact, there's a diagram here. This is the initial side. This is where we start. We have to know where we start and where we finish to define an angle. This is the initial side. This is the finishing point. And then this point where they meet is called the vertex of the angle. So anyway, this is how we start. Yeah, so a degree is 1/360th of the entire rotation of a circle. And so we're going to assume in many cases that we're starting in the so-called standard position, which means the vertex is the origin. Now remember, the origin is the point where both x and y are equal to 0. You might remember that term from your travels. The origin is 0, 0. So we start here with the initial side. So now in this example, it appears to me, just by glancing at it, that we went through the entire first quadrant and halfway into the second quadrant, which means the total amount that we moved is actually 135. So that angle would be 135. The angle formed between the initial side and the terminal side is 135 degrees. Or if you want to think about it this way, it's this fraction of an entire circle. Whatever that number is. That's, let me just quickly double check that number. 135 divided by 360 is 3.375. That's actually 3/8 of the entire circle. So therefore, we call it 135 degrees, but we can think of it as 1/8 of the rotation through the entire circle. All right. I'm sorry, not 1/8, 3/8, right? Okay, so going through each quadrant, 90 degrees means just going through the first quadrant. Now, it turns out, though, that we can have negative angles. With a positive angle, it's understood that we're going in a counterclockwise direction. All right, starting from the x-axis, go counterclockwise. So let me just make a note of that here. Oh, it says it right here. An angle, if we're moving in a counterclockwise direction, the angle is positive, otherwise it is negative. Okay, so we've already discussed this. So negative 135, now you see negative 135 means we're going this direction through the entire fourth quadrant and halfway into the third quadrant. Now, if you notice, we're reaching the same point as if we had gone this way. If we'd gone counterclockwise, we would have covered 90, 90, and 45 degrees. So going in that direction, which is considered to be a positive angle, would bring us to 225. So it turns out that 225 and negative 135 mean the same thing because they bring us to the same side right here. So these angles are said to be coterminal because we end up at the same terminal line. They are equivalent to each other as far as rotation is concerned. And, you can always tell what you should be able to figure out one from the other without too much difficulty. And here's why. Let me just show you another example. Suppose instead we had something like this. Oh, that's so terrible. I'll get it, don't worry. I'm trying to make it look halfway reasonable. It's not as easy with this tablet. All right, I'll tell you what I'll do. I'll fix it like this. So let's just say we went this direction. Ooh, that's terribly badly. Let me just try to take another shot at that. Okay, so what are we getting at here? Starting from this side and ending up here, and we go in a counterclockwise direction, we've gone 210 degrees. I'm sorry, clockwise rather. This is negative 210. Up here, we've gone 150. So the thing to notice here is that you should be able to figure out which is which by looking at a diagram, but also if you notice one interesting result, and this will, once you see this, you'll never forget again. The sum of the absolute value of two coterminal angles is always 360. Okay, because we're thinking in terms of rotation. The angle, the sign is actually irrelevant. So in other words, if you notice 210 and 150 add up to 360, they are coterminal. They have to bring us to the same point. So no matter which one you're given, you should always be able to easily and quickly figure out the coterminal angle for that. Notation wise, I'd not heard of this before I saw this book, but they're saying here that the standard angles, the ones where you go through one quadrant only, are often called quadrantal angles. Quadrant, obviously comes from the word quadrant. I don't think you have to know this, but if you see it, that's what they're talking about. Now, you might remember from your travels that there's an equivalent way of measuring rotation or angles, and that is to, instead of calling them degrees, we call them radians. I always personally found radians to be very confusing because I'd much rather think about degrees, but for some applications, it's easier to deal with radians. And the way it works is that pi radians is 180, and then all the rest are just functions of that. So in other words, 360, the entire circle, contains 2 pi radians. A single radian, based on this definition, is approximately 57.3 degrees. It's a very peculiar amount. So I don't know. I personally prefer to think in terms of degrees, but it's important to be able to do both. Now, your calculators, it's not immediately obvious, and we'll see this as we go along. Your calculators can actually calculate trig functions in terms of both degrees and radians, but you have to know how to do it. So we'll definitely do a lot of that as we go along, but just be aware your calculator can do it either way. So for example, if you came up across an angle of pi over 6 radians, how would you know how many degrees that is? Well, because pi radians is 180, you divide both sides by 6, and that implies that pi over 6 radians must be 30 degrees. So as long as you remember this, you shouldn't have any trouble converting degrees into radians and vice versa. That's the one that you should remember. Pi radians, 180 degrees, half of the circle. Okay. Then the rest just falls right into place. Like, for example, here's 3/4. Well, how many you just multiply both sides of this equation by 3/4, and you'll end up with 135 degrees. Now, by the way, here's another example of these coterminal angles. If you notice, the -1 means we've gone 90, 90, and 40, which means up here in this direction, we went 90 and 50. And you can see these two, the absolute value of -220 plus 140 does in fact add up to 360. So that means they must be coterminal. Coterminal meaning that they both bring us to the same side, the terminal side, that is. All right, they both have a common terminal side. That's why they're called coterminal, because they both have the same starting point too, but we're moving in different directions. The key is that they both end up in the same terminal side. All right, now reference angles. Now, sometimes, let me just show you a diagram here. An angle, because the angle refers to rotations around the circle, you can imagine a situation like this. What if I have an angle of 45 degrees? I'm moving in a traditional counterclockwise direction. What if I instead did this? I went all the way around the circle and then another 45 degrees. the angle that I've just created would be 405. Because it is the same thing, except I went around the circle a full time before I stopped at this terminal point. Well, it stands to reason that these are both considered to be the same angle. So that's where this is going. So now if I went around a second time, let's see if I can draw this properly. Oh, that just made it ugly. I'll just type this. So moving counterclockwise halfway through the first quadrant forms an angle of 45 degrees. Moving through the entire circle, and then another 45 degrees forms an angle of 405 degrees. Both are the same angle because the terminal side is the same. And you can imagine you can do this as many times as you want. I could go around a second time. Oops, not that one. Going around the circle, moving counterclockwise around the circle twice, and then another 45 degrees would form an angle of, and it would be 360 plus 360 plus 45, which is 765. And then this is the same angle too. So therefore, wow, this could potentially get very confusing. Therefore, the following angles are the same. (45), 405, 765, 1125. That's right, isn't it? Yeah. And it just keeps going on and on forever. So it's not convenient to deal with angles like 765 and 1125 and that kind of thing. So what we will typically do is this. It is typically more convenient to describe this angle as 45 degrees than 405 or any of the others. So we define 45 degrees is defined to be the reference angle for 405, 765, etc. Okay, so there's of all the different possible ways we can express that angle, the one that we will typically use is the 45. We can't make it any smaller than that, okay? But that's the one we normally use. So just because it's convenient. So the reference angle is the smallest acute angle, meaning anything below 90, that can be formed from the terminal side and the horizontal axis. So in other words, given that the same angle can have many equivalent angles by just simply going around the circle, for all of those other measures, the one that we really need and use the most often, it would be the smallest. The 45 degrees in this case becomes the reference angle. Now, the same thing holds for radians, except that every time you go around the circle with radians, you're adding 2 pi. So to do the same thing with radians, let's say, for example, draw a picture here. Same picture, except that we're going to have radians moving here. Hold on 1 second. Yeah, the good old tablet has suddenly decided to stop working. It happens every so often. Now 45 degrees, as you recall, would be pi over 4 radians. So if I move in this direction, pi over 4, going around the entire circle and coming back to that point would be 2 pi plus 4, pi over 4 rather, which would be 9/4 pi. But they mean the same thing. Okay, so what this is saying is that pi over 4 and are the same angle. So we choose pi over 4, the smallest, to be the reference angle. Yes, so there's a chart here for this. So you can see exactly how this works. No, they are the same angle. That's the whole point. So the reference is calculated in the following way. So let's do one in the third quadrant just to see. So let's say we go into the third quadrant. Let's say halfway. Oh, actually, sorry, that's the second quadrant. Hold on. So 180 is pi over 2. Each quadrant is pi over 2 when we're dealing with radians. This one is pi over 4. So by the time you get to this point, you've actually gone 5/4 pi. If you go around the circle again and come back to that same point, this one is 2 pi plus 5 pi over 4, which is 13/4 pi. So they are the same thing because they're different by 2 pi. Just like before with the angles, it was 360. So that means that 5/4 pi is the reference angle for 13 pi over 4. So they're all the same. All right. And one more thing here, the coterminal angles. Remember, we talked about coterminal angles with degrees. In a similar way, we can do the same thing by subtracting 2 pi from an angle until it is smaller than 2 pi. Okay, so we have the concept of coterminal with radians as well as angles. All right, now, what's coming up next is we're going to introduce something called the unit circle. This is the circle where we have the start at the origin and the radius is 1. Okay, so you might recall that the diameter of a circle here's your circle. Let's try that again. Okay, so the diameter would be the line that cuts to the entire, or cuts the circle in half, basically. And then this would be your radius. So this line, and it could reach to any point in the circle. It's a circle where the radius is a constant one all the way throughout, no matter where we start. I mean, as long as we start at the origin, that is, any point that we touch, the radius is just 1. So this is going to prove to be very helpful for deriving formulas for calculating sines and cosines. And once we know those two, we can easily calculate the rest. So if you go back to the beginning, for example, I just want to quickly mention, and we'll see there's a lot of identities with these trig functions. But as you can see, if you know the sine, you know the cosine, cosecant. If you know the cosine, you know the secant. Here's an interesting result, though. The tangent itself can be derived directly from the sine and the cosine. In fact, the tangent is just the sine over the cosine, because that gives us over h over a over h, and the h's cancel out and we're left with over a. So what that means then is that you only really need these two to derive the rest. Once you know the sine and the cosine, you can figure out the tangent. Once you know the tangent, you can invert it, you get the cotangent. The cosecant and the secant are themselves just inverses of the sine and cosine. So we're going to see a technique that lets us calculate the sine and the cosine for different angles based on the so-called unit circle. And it'll be based on what we're seeing here. The idea that the sine is simply the opposite over the hypotenuse, and the cosine is the adjacent over the hypotenuse. We also want to remember, of course, the Pythagorean theorem. As you have, I'm sure nobody has ever forgotten the Pythagorean theorem. For any right triangle, there it is, our old friend, the Pythagorean theorem, which has many implications. Okay. This isn't, I mean, this is the starting point, but you'll see it implies a lot of other interesting results. But that is also the basis of what we're about to do. Okay, so we're going to try to do is come up with a strategy which the ancient Greeks would have had to use to come up with all their results. They themselves they were very good at geometry. A lot of the algebraic results that we take for granted now were invented much later. The Greeks were focused on geometry. All the results were derived that way. So let's see, where were we? All right, yes, the unit circle, yes. So we know what the sine and cosine are. So here's a specific example of a right triangle, 1, 2, radical 3. You may have seen this one before, and you can see that in fact it does conform to the Pythagorean theorem, because 1 squared plus radical 3 squared equals 2 squared. 1 plus 3 equals 4. Oh, yes, it does. So this is a standard right triangle. Now, what angle is this? Well, we're going to find out. Okay, so now, based on this information, though, we can easily calculate all the trig functions for theta, whatever angle that is. So I'll tell you what, let me copy this. I want to see if I can, it would be nice if we could refer to it. Let's see what I can do. All right, well, you know, it's there. It's kind of hard to see it, but what I'll tell you what, let's try this. All right, well, that'll do. All right, so in other words, the sine of theta is the opposite of the hypotenuse. This would be the opposite, and this would be the hypotenuse. And that's how it's done, okay? So equivalently, the actually, let me move this a little so I can make space for both of them. The cosine, the adjacent angle would be this, adjacent side is this one. Okay. And as we saw before, we now can calculate all of the others directly from these results. But if you wanted to, what you could do instead is find the tangent, for example. Opposite is 1, adjacent is radical 3. And then you will, of course, turn that into radical 3 over 3. Okay. All right, and then the other 3 that we saw are just the inverses of these 3. So it's not difficult to do this based on, of course, our old friend, the Pythagorean theorem. Now, this is where it gets interesting. This is the right triangle with angle T. Because this is a unit circle, what that implies is that let's see, the two sides are equal. Oh, actually, no, let's label it like this. Relative to T, this is our adjacent side. And this is our opposite, and this is our hypotenuse. Actually, you know what? Maybe I'll draw a bigger picture of this, just so we can get a closer look at it. So remember, we're assuming this is the unit circle. The radius is 1. The radius is clearly the hypotenuse of this triangle. We don't know what the other 2 are. This is, for this angle, T, they're calling it. This is our adjacent side, and this is our opposite side. So therefore, since the sine of T is O over A, oh, sorry, over H, but H is 1, defined to be 1. that implies that this O, the length of this, or the height of this triangle, is the sine of t. And that in turn implies that this is the y coordinate of this point. Now, the cosine of t is adjacent over hypotenuse, or in this case, a over 1, which is just a. So therefore, the adjacent side equals the cosine of t. And that implies that that is the x coordinate of this point. Okay, well, that's getting interesting. So we have a radius of 1, which means that for this angle that we just defined, that point right here, all right, let's not let that happen again. This point has an x coordinate and a y coordinate. The x coordinate is the cosine of t, and the y coordinate is the sine of t. Okay, so that's what's going to be the basis for what's following. So in other words, we're going to see how to calculate sines and cosines based on this right triangle, with the understanding that the radius is 1. So we're just going to do a few of them. We're going to do a few of the standard ones, like 30 and 60 and 90. Well, not 90, but 30 and 60, just to get a feel for this. So let's try this one. So here's a right triangle where we have two equal angles. This is called an equilateral triangle because it implies that both x and y are equal to each other. So the question is, how can we use this information to solve for the sine of 45 and the cosine of 45? Okay, well, let's see. Algebraically, we don't know what x and y are, but we do know that they're equal to each other because these angles are the same. And it shows it right here. XY means XX. It's the same thing. And remember, we already showed this is the cosine of 45. And this is the sine. So we're going to algebraically solve for these by doing the following. Based on the Pythagorean theorem, this tells me that x squared plus y squared equals 1 and x equals y. And we can use that information to solve for x and y. And by doing that, we'll also know the cosine and the sine of both 45 degrees. All right, so the algebra is presented on the next page or slide. So based on the Pythagorean theorem, and again, let me reproduce this diagram so we can follow along. Let me sneak this in here real fast. And the angles are both 45 degrees. Okay. So because of that, we know that the Pythagorean theorem is here. We're going to replace y squared with x squared. And we end up with x squared plus x squared equals 1. So we're solving these with substitution. 2x squared equals 1. X squared is 1/2. X equals plus and minus radical 1/2. But since we're in the first quadrant, x is positive. So therefore, x must be positive radical 1/2. Okay, so therefore, And since they're equal to each other, they must both be radical 1/2. Now, of course, we don't like to leave it like that. So I'm showing you on this graph here, this slide, this is equal to this. So what we just shown is that sine 45 is radical 2/2, and cosine 45 is also radical 2/2. Now, if you go to your calculator, the iPhone that is, radical 2/2 is approximately equal to 0.7071, let's say. So let's get some practice here. Take out the iPhone, and what you're going to do is type for the first one. Hold on. I have to remind myself how it works on this. Okay, so here's what you have to do. First of all, make sure that it's in the right mode. Now, you may not have ever noticed this before, but on the very bottom left-hand corner, there's a button that says either degree or radian. Hold on one second. So on the iPhone calculator, there is a button in the extreme lower left-hand corner that toggles between. It either says RAD for radians, or degree. If the calculator shows rad, hit this button. No, actually, if it says rad, you're all set. It's very strange the way they've done this, in my opinion. It is in degrees mode. I really don't get their logic here. Type 45 sine to obtain 0.7071. If it shows degree, hit this button to switch to rad before proceeding. I think this is a terrible decision on their part, because when you see that degree staring you in the face, you assume you're in degree mode, but it's actually the other way around. So I think that they need to rethink this one. But if you do hit the rad button and it says degree, yeah, I don't know what they're doing, but that's how it works. You can confirm that the sine or the cosine, do the same thing with cosine, are both 0.7071, which is radical 2/2. Now, if you want to do an experiment here, just to get some practice, since 45 degrees equals pi/4 radians, Try switching to the radians mode and solving for cosine pi over 4 and cosine. And they'll have to be the same. Whether they're measured in radians or not, it's the same angle. So let's try that. Switch to the other mode, the radians mode. And then put pi over 4. Now there's a pi button on here too, by the way. It's very well concealed. Where is it? Oh, you know what it is? It's very close to the 0. Make pi over 4 and then hit the sine button and then do the same thing for the cosine button. And you'll see you do get the same thing. Okay, so that's how you know. I noticed too that when you're in the radians mode, it actually has a little RAD sitting on top of their parentheses. I guess that's their way of telling you that it's in radian mode. I think they've set it up very strangely, but there it is. So in principle, now the reason why this is so important is because in principle, you can now calculate any trig functions you want. Now, if you notice, it does also have tangents, but it doesn't have the other three. It doesn't have the cosecant, it doesn't have the secant, it doesn't have the cotangent. I guess they figure if you want those, you must be smart enough to know that they're inverses of the basic functions. So yeah, there's a proof here for 30 degrees too. I think we'll skip over this because we don't really need to. I just wanted you to see how this is done. So instead, here's a table. What you might want to do at some point is go through here and confirm that you can get these on your calculator, and just be aware that the calculator will give you the decimal equivalents here. So you'll have to calculate those first, but just to make sure you have enough practice doing this, at the very least, you should try to reproduce these numbers in the degrees mode. And yeah, I mean, you can see in principle, this unit circle, if you know what you're doing, can be used to solve for any angle you want. But you can see it's going to take a lot of cleverness to set up a triangle that meets your needs. So, and here's a list of everything, but once you understand how they're defined, it's enough to be able to do them on your calculator, okay? That's all we can really ask for here. Now, a couple of other important details here. The domain of a sine or a cosine is all the real numbers, but the range is the interval between -1 and 1. So why don't we do this? Let's take a quick look at Symbolab and see why this is. All right, we'll start with the sine, and then we'll do the cosine. And you can visually see why the range is between 1 and -1. Let's get this out of the way. All right, here we go. Y equals sine x. Let's take a look at the picture. And you'll see something interesting. This function is cyclical. Look at that. It keeps repeating over and over again. And if you notice, it never goes above 1, but it does actually reach 1 at this point. And it never goes below -1. So it does touch on those two. So they're not asymptotes, but it never goes outside that range. Whereas with they're defined for all x's, the function can only go as high as 1 or down to -1. Same thing for the cosine. It's basically the same thing, except this cycle is off a little bit. In other words, if you look, it just starts and ends at different points, but it's the same thing. Now, the tangent is very different. There are actual asymptotes for the tangent. There are values of x in which the tangent is undefined. So for that one, you can see it's a much more complicated situation. So let's see. Yeah, see what I mean? Look, there's actually quite a few asymptotes for the tangent, although you can see that the range is unlimited. It goes all the way from positive to negative infinity. This time it's the domain that has holes in it because of all those asymptotes, okay? And of course, you can imagine what the inverses look like. So here we're defining, we've already discussed this basically, we don't have to do this again, how to define tangent from the sine and cosine, cotangent, which since it's 1 over tangent, it implies that this is also equal to the cosine over the sine. Secant can also be written as 1 over the cosine, as we've seen, and then finally cosecant is 1 over the sine. All right, so we only have a handful more topics. So here's what we're going to do. We're going to have our break. And when we get back, we're going to actually wrap this up really quickly. And then because we don't have all the time in the world, we're going to go on to our next topic, which is 11. Now, remember, next week, so yeah, let's remind ourselves, the test is going to have to be on the 16th in 2 weeks. So that means we have 1 week next week to do the chapter 5 problem set, which is on Moodle, by the way. Everything is on Moodle right now, I believe. I'll double check, but I'm pretty confident it's all there. Actually, I'll do it right now. We don't want any issues, do we? Hold on, I'll just confirm this. And so the next chapter is actually 11. Now, 11 is a very applied chapter. I mean, it may seem a little theoretical at first, but it has a lot of practical uses. Okay, so let's go to Moodle. And let's see. Yes, it is there, but you know it's missing the sample midterm. I better get that in there right now. Because yeah, it's so, I've got the same class on Mondays and Thursdays in the normal twice a week mode. And so it's hard to, or it's easy to forget that we really only have a couple more weeks before the exams. So we have to be super careful here. There it is. Okay. Let's take a look at it. So there's all this discussion about logs and exponential functions. And oh, wait a minute. Where's all the trig questions? Oh, all right. I'll tell you what, I better take a look at that. I'm kind of surprised to see that. I thought that there would be a bunch of trig questions. All right, I'll work on that and get it posted tonight. Okay. I don't know what happened, but so we'll save that for just a little bit longer. But yeah, because it has to include chapter 5. Now, chapter 5 problem set. Let's see what it contains. Yeah, it's all just trig functions. Okay, so we'll do that and the sample midterm. I'll get that thing together probably tonight. So that way you'll have them both and we'll work on them for next time. But in the meantime, 11 is our next chapter. We're skipping over some more complicated topics because I want to get to something that's more practical. And actually, it's a very interesting topic that we'll be looking at. We're basically introducing ourselves to probability theory, which I think you'll see when we start it is actually quite interesting. All right, hold on. There it is. It's actually more than even just probability theory. We're introducing what's called combinatorics, which is the science of counting. So it's a long chapter, but there's a lot of very interesting topics in here. Maybe not quite as abstract as what we've been doing. And then when that's done, and this is only on the final, by the way. Let me do one thing here. The reason why, yeah, the PDF is important because if you have a Mac, it's possible that some of this information will not show up properly on a PowerPoint slide. So that's why I like to always have the PDFs as well. So as soon as that's ready, I'll post it. Because we're going to, as soon as we're done with 5, we're going to dive right into this because again, we don't have time to waste. Okay, this is going to take a minute. All right, I'll tell you what, while we're waiting, why don't you go and start your break? We'll have our usual half-an-hour break. When we get back, we'll wrap up 5, though there isn't too much left to do. A few identities basically, and then we'll dive into 11 rather. Okay, with the understanding that next week we'll be doing the chapter 5 problem set and the sample midterm, so that the week after we can have midterm number 2. All right, so I'll see you in about half an hour. Actually, I think I can pause the sharing so that people who are watching this aren't going to see a half an hour of blank space. There we go.
I tried and crap me tell say me I graduate and then they tell her say she and then she remember me used to call and talk to Todd because Todd used to cry about me and him beat Todd and so Todd mustn't talk to me. And me and say, my God, you know what me could have do? This lady. So send me breathe and you send me the stuff so me pregnant or whatever. What pretty people are pregnant or whatever the case maybe. I mean, me wasn't no horrible kind of person. After such when you come, me wash, cook, clean, take care of things when the boy them they apart. Then I said, me I do one work, me I do much something, me I like tutor Mikey little boy. Mikey, and me teach Mikey first son to read in 1 week. And then he's supposed to give me must have been on my friendship with that. Afterward, Mikey started coming with one of that boy with two picking them at two different mother and they pick they don't know about each other. And one little 7, 6 year big one of that night
So again, we just have to finish up a few more topics, very few in chapter 5 before we dive into 11. So we just want to mention here, earlier on, at some point, we had a discussion about even and odd functions. Sorry, where a function is even if for every f of x, f of x equals f of negative x. A classic example of this would be the absolute value function, because let me just sneak that in here. Y equals absolute value of x is an even function. And here's why, because no matter what value you take, let's say, so this is the definition of even. So the absolute value, let's say, of 3 equals the absolute value of negative 3. So that's what it means for the function to be even. Okay. As far as odd goes, an example of that would be let's say y equals x cubed. So the definition of odd is this one. Now for this one, this is the odd function. So our example would be x cubed yeah, I have to do an exponent here. It's still a little awkward to do exponents in PowerPoint. So for example, let's say f of x is f of 3 would be 3 cubed, which is 27. That being the case, negative f of negative 3 would be negative 3 cubed which is the same thing as saying negative. Now, negative 3 cubed is negative 27. So therefore, this ends up at 27. So these are two examples of what we mean by odd and even functions. So what we're saying here is that the trig functions, many of them are even and many of them are odd. So let's take a look at this list for a second. Sine and cosine, sorry, not sine and cosine. Cosine and secant are even. The rest of them are odd. Okay, so that's just something we want to mention here. I don't know if you can really see it from a graph, but these, if you want to confirm these, you can take any angle and plug it in here, and you'll see that this is in fact correct. So we've got two even functions. Oh, let me do one thing here. There we go. Now it makes sense. Okay, so we have two odds, two evens and four odds. Okay, now trig identities. We've started to discuss this as well. Sometimes recognizing how these trig functions are identified or defined can help us simplify complicated expressions. And some of these we've already looked at. For example, we know that the tangent is equal to sine over cosine. The secant is simply the inverse of the cosine. The cosecant is 1 over the sine. So what this implies is that the cotangent, which is 1 over the tangent, is cosine over sine. So here's a good example of what I mean. Suppose you had an answer to a question like this: secant t over tangent t. Well, if you use these identities, what you'll discover is that those two cosines cancel each other out, and we actually wind up with the cosecant of t. And so, like with every other case we've ever run into, simpler is always better. So, if you have an answer like secant t over tangent t, you're probably better off just writing it as the cosecant, because then it's obviously a simpler version of the same thing. So with trig functions, we can often lean on these identities to help us simplify our results, either that or make it easier to solve for the equation. Now, here's another chart that I found on the internet somewhere, just so if you needed a quick glance at these results. This one is different because it has all 6 trig functions. Many of these charts only have the first 3. So you can see, and of course, it only shows the standard cases, 0, 30, 45, 60, and 90. And you can also see that there are cases where the tangent, the secant, the cosecant, and the cotangent can be undefined because of division by 0. We can see the answers themselves. Most of them either involve radical 3 or radical 2, although in some cases the answers are 1 or possibly 2. And also, as far as the Pythagorean identity is concerned, we already know how that works. The Pythagorean theorem tells us that a squared plus b squared equals c squared. But in terms of trig functions, that has a lot of interesting implications. One of them being that the cosine squared of any angle plus the sine squared of any angle equals 1. And this is a direct consequence of the Pythagorean theorem. So no matter what that angle is, the sum of the squared cosine and the squared sine will always add up to exactly 1. And this in turn can be used using the identities to derive a couple of other identities that could potentially come in handy. For example, it turns out that 1 plus the tangent squared equals the secant squared. And how do we do that? We took this expression and divided it across by cosine squared, and using the identities that we know, we end up with this result. Now, if we take the same starting point, actually, let me leave it there for a second so you can copy it if you want. We probably won't have any problems this complicated. But it's good to know that this works. In other words, you may end up with a messy problem. And, you might start to think, well, are there ways I can simplify this simply by using these trig identities? And, you never know what you might find. Now, if you take the same Pythagorean identity and divide by sine squared, we end up with this result. The cotangent squared plus 1 equals the cosecant squared. So, this can often come in handy if you end up with an answer that has both cotangents and cosecants in it. All right, so that's all we need to say here about trig functions. So let's move on to 11, which is where we're going to be looking at a couple of different things. We're going to be looking at a branch of mathematics called combinatorics, which is basically the science of counting, which is a lot more complicated than it sounds, believe it or not. You might think, wow, we know how to count, but it's a very complex, but very interesting and useful area. And that will lead us to our discussion about probability theory, which has so many applications in the real world. All right, first let me save this. So I'm going to post these. If this is the version where I've been writing on the screen, so I want to save this so we don't lose anything. And then I'll post this on Moodle. As soon as it's ready. So this will be, think of this as an alternative version of chapter 5. All right, so let's see, is it ready? It takes a while because the handwriting apparently sucks up an awful lot of memory. Yeah, it's gone. There it is. Yeah, it's taken a while. Also, there's a lot of graphs. If you notice, I found a lot of graphs and I pasted them in there. That also swallows up a lot of memory. So this is the original, and you can see there's some, potentially useful notes. And then here's the copy that they made. Yeah, because, in order to do this, so you have to have the Adobe. It's not enough to have the Adobe Reader. You have to have the what's called the Adobe Acrobat, which you can buy separately, or you can get it as part of the what do they call their creative suite, which includes things like Photoshop and all the others. So if that's what you're into, if you already have Photoshop, for example, you might be able to get a cheaper copy of Adobe Acrobat, and then you can create your own PDF files. All right, let me just do one more thing. I just want to make sure that I get these into Moodle before I forget. All right, here we go. And I put dates on here so you know which one we're talking about. These are the notes that we did today. All right, so you've got the original 5 and you've got these. You've got the problem sets, you've got the solutions to 4. The problem set is here. I'm gonna work on that sample midterm and make sure it's up there by tonight. So you can work on that between now and next week. And then here's 11. So it looks like we're all caught up here. Very good. All right, let's get 11. So we're going to look at some very important topics here. And these are all actually very useful in the area of computer science. Okay, calculus is very useful in a lot of applications, but not so much in computer science because calculus is a continuous type of math, whereas computer science is really a discrete form of math in the sense that you have to deal with countable sets with computer science, whereas with calculus, you're dealing with infinite sets. So these are all topics you might run across in a computer science course, or at least a course that's meant to introduce you to the mathematics of computer science. Or sometimes a course like that might be called finite math, it might be called discrete math or something like that. But these topics are typically included in a course like that. So we're going to be looking at sequences, probability theory, and counting theory, or combinatorics as it's called. Okay, so we'll start with the sequences. Now, sequences are a very simple idea. What you actually have here is a string of numbers that have a common pattern between them. In other words, if you notice, I've got the numbers 1 through 6, and I've got the 3 dots there, which indicates that this carries on forever. And you should be able to tell just by looking at the numbers what comes next. The idea here is that there's a pattern there that will repeat forever. And so our job is to figure out what that pattern is. So in a case like the one you're looking at now, it's very simple to see that the next term in the sequence would be 7. Now, how do we know that? What gives it away? Well, if you notice, how did we get to this point in the first place? We started with 1, and then to get to the next term, we simply added 1. Okay, then we went to 3, 4, 5, 6, and then we ended up with 7 next, and then 8, and then 9. So this is a very special type of sequence. And so, by the way, in this section, we'll be focusing on 2 types of sequences. The first type are known as arithmetic, and the second type are known as geometric. So the example I just showed you is actually an arithmetic sequence. And how do we know that? Because the terms have a common difference between them. Okay, what does that mean? It means that in order to go from one term to the next, I just keep adding 1. Right? So now that is an example of an arithmetic sequence. So let's look at some more of them. We have this first one, arithmetic, because we're just adding 1 to each term. The second one is also arithmetic because as we move through the list, you can see that I keep adding 3 to each term to get to the next one. And the third one too, even though the numbers are shrinking, that indicates that we're subtracting 1 from each term to get to the next one. So we can either add or subtract, and we still call it an arithmetic sequence. We can start at any point, by the way. As you can see, the starting term, the first term doesn't have to be 1. It can be any number. And by the way, it doesn't even have to be an integer. These are very simple cases, but they could be fractions, they could be negatives, they could be anything. As long as there's a common difference between the terms, it then becomes what we call an arithmetic sequence. Now, even though that it's easy to see where these terms are going, there might be cases where, let's say you're looking at it and you need to know, let's say, what is the 20th term? Well, you have 2 options then. You can just write them out, but that could take a while and it's prone to mistakes. So if there's only a formula that we could use, that might speed things up a bit. And it turns out that there is indeed a formula to do this. What does that formula look like? Well, let's take a look at it. So in order to find a specific term in an arithmetic sequence, we're going to use this formula. Now, the A's are going to be used, AI will be used to represent the term I. Okay, so that means that A1 is the first term. AN is the nth term, as we call it. N is determined by us. We are the ones who decide which term we're looking for. So let's say we're looking for the 7th term, then that would actually be A7. N is the term that we're looking for. Again, here's the N. D is the common difference between the terms. Okay, so whatever number separates all the terms is that D. So this formula will enable us to figure out any term we need as long as we know the starting term and the common difference. It's not very complicated either, but it can find us any term we want. It doesn't matter if it's term 2 or 6 or 500, it doesn't matter. It's an easy thing to do. So let's just look at a quick example of this. So here's an arithmetic sequence. Let me just write down the formula again. And we're asking, what is the 10th term in the sequence? Okay, now clearly, the first term is 1. D, the common difference is 5. N is 10 because we're looking for the 10th term. Okay, so what are we going to do to solve for this? Well, AN, A10 equals A1, which is 1, plus 10 minus 1 times D, which is 5, 1 plus 45 is 46. So if we stretch this out to 10 terms, we'll see that the 10th term is indeed 46. Okay, so you can see, again, you're looking for the 10th term. We started with 1, and then n is 10, so we have 10 minus 1. The common difference between the terms is 5, so that implies that the 10th term must be 46. Okay, so on the next slide, I've shown you the actual terms, and you can look at it and say, oh yeah, you're right. It must be 46. Okay. And so again, you have the option of doing it either way. But I think that when you get further along into the sequence, there comes a point where it makes a lot more sense to use the formula than just write them out. Although you can certainly double check one with the other if you want to. Now here, it's the same thing. It's already written into the slides. It's 46, okay. Now here's another one. Now this time, you can see that the starting value or first term is 2. The common difference is 4. And we're trying to find the 9th term. So remember, our formula is AN, it's A1, N minus 1D. So therefore, A9 is 2 plus 9 minus 1 times 4, 2 plus 8 times 4, 2 plus 32 is 34. All right. All right, so everyone sees how that was done. And of course, on the next slide down, we're going to see this confirmed. Oh, maybe not. It looks like I didn't do that. So I'll do it right here. Ah, there we go. Number 9 is actually 34, so we're good. Okay. Now, oh, I need to do one more thing. Hold on. Another thing that we often may need to know is not so much the nth term, but the sum of the first n terms, which would be a major headache if we have enough terms. But luckily, we have this formula that we can use to do this directly. So Sn will be defined to mean the sum of the first n terms. Okay. And then, but of course, if you notice, we need to know the values of the first term and the nth term in order to do this. All right, well, let's do one. Okay, it's not horribly complicated, but it's a little messier than what we were just doing. So here's a case where we have the following sequence. And in fact, let me just copy this. We're looking at the sequence 1, 3, 5, 7, 9, 11. All right, so this is what we're going to do ultimately. And the question is, what is the sum of the first 5 terms? Well, I mean, you can do it yourselves. It's on the next slide. You'll see that the sum of the first 5 terms is just 25. Okay. But, even with 5 terms, you can make mistakes. So you might want to use this instead. So then we have to identify the different components. A1 is 1. A5 is 9. And N itself is 5 because we're looking for 5 terms. We'll have so S5 is 5 times 1 plus 9 over 2. $25. Oh, there you go. So that means we must have done it correctly. I mean, you can see that either way, you get 25. All right, so that wasn't that bad. So let's do another one. So for this one, we're looking for the first 6 terms. Okay, now the answer is on the next slide, so let's do this. If n is 6, A1 is 8, A6 is 18, and what we want to do is solve for S6. We'll have 6, 8 plus 18 all over 2. So the 6 and 2 divided by 2 is 3. 6 times 20, 3 times 26. So we do in fact wind up with 78. Now, again, if you want, you can just take out a calculator and say 8 plus 10 plus 12 plus 14 plus 16 plus 18, but you don't really need to because you have this formula. All right. And that's what we did on the next slide. And then here's the formula. Now, so again, all of these cases involve what we call arithmetic sequences because we have a common difference between the terms. We also have another type of sequence called a geometric sequence, where instead of adding numbers to get from one term to the next, we're multiplying them by a common ratio, as it's called. Which means that the terms are going to get very large. Typically, will get large very quickly, depending on what they're being multiplied by. So let me show you some examples of this. In the first case, clearly, each number is being doubled. So the ratio, we'll call it R is 2. In the second case, each number is being multiplied by 3. And in the last case, each is being multiplied by 5. All right. And so that's how you know that they're geometric. And you can tell just by looking at them. They're getting very big in a hurry. Arithmetic sequences just do not grow that fast. Okay. And once again, you can start with any number. Any term can come first. Also, I just want to point out these ratios can be negative and they can also be fractions. They don't have to be integers and they don't have to be positive. All right, so now, just like with the arithmetic sequences, we are going to need to define 2 formulas. One of them, which will enable us to find a particular term in the sequence, and the other one to find the sum of the first n terms. The formulas are a little different. And if you look at them carefully, you'll see that they do not involve the difference because there isn't one. So for example, the formula for calculating the nth term in a geometric sequence looks like this. And so here, all you need is the first term and then the common ratio. So it's actually a very simple formula, surprisingly enough, considering how complicated these terms are. So I'm going to copy this onto the next slide. Maybe I can make it a little bigger. And so let's try this one. What is the 7th term of the sequence? Now, clearly, in this case, R is 2. And A1 is 1. The seventh term would be calculated as follows. So you just end up with 2 to the 6th, which is 64. All right. So we can confirm that by just writing them out. And yes, indeed, this is term number 7. That's what we're aiming for. Okay. Let's try another one. Here we go. So here we've got now, first of all, you should make sure that it is in fact a geometric sequence. You can see that each time the numbers are being multiplied by 3. So it is a geometric sequence, and we're trying to find the 5th term. Now you can see for yourselves just by looking at it, the next term must be 243, but let's use the formula. A5 is, A1 is 3. So the ratio is 3 and the first term is 3. So you have 3 times 3 raised to the 5 minus 1 power. But that means you actually have 3 to the 5th power. And that's equal to 243 as we predicted. Right? You take out your calculator, 3 to the 5th. $243, exactly. Now, just like before, in addition to finding a specific term in our sequence, we often want to know what is the sum of the first n terms. And so this is the formula. Now, you can see, in this case, we're interested mainly in the ratio and n. We don't actually need to know the term an in this case. So this is our formula. And now here's the sequence. And you can see that in this sequence, the first term is 5. And the common ratio is 2. We're doubling as we go along. Now, some of the first 4 terms is, you can see, I mean, you can look at them yourselves and add them up and you'll get 75, but let's do it with a formula. So 2 to the 4th is 16. So this is 5 times minus 15 over minus 1. The negatives cancel and we end up with 75. There you go, which is obtained, could have been obtained by 5 plus 10 plus 20 plus 40 equals 75. Okay, so I think that's enough that we need to say about sequences. So now we're going to move on to the combinatorics or counting principles. And this will introduce some topics that you might not have run into before. We're going to start with this notion of the fundamental counting principle. So this refers to the number of ways in which a group of objects can be arranged. So what do we mean by that? All right. Just as a quick example, and then we'll do another example after this. Suppose that you had the following information. Suppose you have three posters. Oh, okay. And room for hanging to all three. Okay. Now, here's the thing. The posters are 1, 2, and 3. Okay, now obviously you don't have a poster of number 1, of 2, or number 3. We're just going to call them that. So how many ways can the posters be hung? So you just have to imagine you've got a wall with room for 3 posters. And so let's say, for example, you can hang them from in this order, number 1, followed by number 2, followed by number 3. What else could you do? Oh yeah, that's a possibility. Okay, what else? And then what about this one? So there's actually 6 different ways we can hang our posters. So each of these choices is known as an arrangement. Because we're taking a group of numbers and rearranging their order. So there are 6 different ways I can write 3 different numbers. Each of these choices is called an arrangement. Now, the next example is an even more fun one because now this is down the road. This is right now, 3 posters in your room. What about this case where you have a 3-car garage at your mansion and you need to figure out how many ways you can park your 3 cars in there? You could have your Infiniti, your Lexus, and your Mercedes, and you could put any car in one of these 3 garages. So the list of possibilities looks like this. Well, of course, there's 6 of them again. There have to be 6. So each way to park the cars is known as an arrangement. Now, here's a good question. Why is it 6? Is there a way we can base our choice on logic rather than writing them all out? And the answer is yes. And here's how we have to think about it. So let's add a new slide here. For the posters example, there are 3 choices for the first poster. Okay, in other words, you've got the one on the far left, you've got 3 posters, you can pick any one of those. Once a poster has been chosen, there are 2 choices for the second poster. Once these first 2 posters have been chosen, there's only one left. for the third poster. The total number of possibilities or arrangements, as we call them, is therefore 3 times 2 times 1, which is 6. That's where that comes from. It's 3 times 2 times 1. Now, what if there had been 4 posters? Well, what would have happened differently? With 4 posters, there are 4 choices for the first poster, 3 choices for the second poster, 2 choices for the third poster, and then 1 choice for the last poster. Total. So the total number of possibilities then, in this case, is going to be a lot larger. It's not 6, but let's see what it is. The total number of choices, or the total number of possible arrangements, is, and then you could probably guess, it's 4 times 3 times 2 times 1, which is 24. So there's a logic here that we will be able to express with a mathematical operator that you may or may not have seen before. So that operator is known as factorial. Now, this is interesting. It's on your calculator, by the way. If you look, although it's listed as x factorial on your calculator, if you look very carefully, you'll see it way down, almost, it's to the left of the sign button, but it's in the extreme left-hand corner. And so the factorial operator is defined for exactly situations like this. We write the exclamation point. In English, we pronounce that as x factorial. And it's defined in the following way. First, it only applies to non-negative integers. And so 0 and 1 factorial are both equal to 1. After that, it gets interesting, though. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, or 6. 4 factorial is 4 times 3 times 2 times 1. And you can see how this goes on and on and on. 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. 6 factorial, 6, 5, 4, 3, 2, 1. So every time I increase the factorial, I'm multiplying it by a new number. And it gets large in a real hurry. For example, if you went to your calculator to do 10 factorial, on this calculator, you would type 10 followed by that factorial button. So write 10, use the 10x. Now, it doesn't even ask you for the equal sign. Just type 10 followed by that button, and you'll get 3,628,800. If you now go on to 30 factorial, it'll get so big that it needs scientific notation. That number you're seeing there at the end, E32, means times 10 to the 32nd power. Wow, that's a big number. It's getting enormous, okay? So this one application of this factorial operator is to tell us how many different arrangements can be created with that number of objects. So if you go back and revisit the cars, the reason why we had 6 ways of parking them is because that's equal to 3 factorial. 3 cars means that 3 factorial, or 6, is how many ways we can park them. Same thing with the posters. We had 3 posters. Therefore, it must be possible to hang them in 6 different ways because that's 6 factorial. 3 factorial, sorry, which is 6. Okay. Now, here's another simple example. We have a small museum with enough wall space to hang 4 new paintings from a famous artist. Okay, this is what he does. This is his specialty. He puts a dot of color on a white canvas. And so those are 4 of his new paintings that are all the rage in the artistic community. And so the question is, how many ways can the gallery, or the museum rather, show them? And so because there's 4 of them, we already know that the answer is 4 factorial, which is 24. It's how many ways we can hang these paintings on the wall. All right, and just in general, there are n factorial ways of arranging n objects. All right, well, so far so good. Now we can increase this to a more interesting case. Imagine that instead of just arranging objects, taking the same ones and changing the order, I'm actually choosing objects from a larger group. I might want to know how many ways I can choose or how many choices I have when I pick a certain number of objects from a larger collection. So if I'm choosing objects from a larger collection in such a way that the order of selection matters, each choice is known as a permutation. So we're going to see how that works. And the formula for permutations will involve factorials, as it turns out. All right, so here's an example. Imagine the following situation. The students at SUNY Purchase decide to start up a math club. There are 10 members of the club, and we have to pick, in order to satisfy the rules of the school, we have to have 3 officers. We have to have a president, a vice president, and a treasurer. So imagine that nobody volunteers for these jobs, so they have to be assigned at random. We have to have somebody in these positions in order for the school to grant permission to have the club. So what we're going to do, because nobody is volunteering, we're going to assign each member a number from 1 to 10, and then we're going to randomly pick 3 numbers so that the first number we pick is the president, the second is the vice president, and the third is the treasurer. So here's one possible outcome of this 317. So I mean, student number 3 is now the president, number 1 is the vice president, and number 7 is the treasurer. Okay, now what if we'd chosen the same numbers but in a different sequence? For example, what if we'd chosen 731? Now, even though they're the same 3 numbers, they're picked in a different order, which means now all of a sudden student number 7 is the president, 3 is the vice president, and number 1 is the treasurer. So that tells us that the order in which we choose these does matter in some important way. You know, it would be different if, let's say, I've decided to, let's say that instead I have 3 free tickets to a concert, and I'm going to randomly pick 3 people to get those tickets. And I pick students 3, 1, and 7. Well, in this case, it doesn't really matter what order I pick them in, because 317 and 731 both mean that those same 3 students are going to get the tickets. But with this math club, the order does matter. It matters a great deal because it determines who will fill each slot. So each choice here is known as a permutation. Now, here's the question. How many different ways can these 3 slots be filled, given that there are 10 members and 3 jobs to fill? Well, for that, we need a special formula, which I'll show you now. And you can see in the top, NPR stands for number of permutations. N is the number of objects that we're choosing from, and R is the number of objects that we're choosing. Okay, so it's understood that R is less than or equal to N. So in our case, with the students, N is 10 because we're choosing from 10 students, and 3 is R because 3 of them will be chosen to be officers. Now it's just a question of plugging them in. Okay, once we got that straight, once we recognize that these are permutations because the order matters, and once we understand that n is 10 and r is 3, we just plug them in, and this is what we'll get. Now, if you notice in the denominator, it's n minus r factorial. So we have 10 factorial over 7 factorial. And that gives me a ratio of 3,628,800 over 5,040, which means there are 720 ways to fill these positions. Now, we're not going to list them all. I mean, but in a case like this, it would be crazy to just write them down rather than try to use a simple formula like this. Okay. So that's why this formula can be so important, because it can save us a lot of time. I mean, a lot of time. All right, now, what about the case where the order does not matter? Like I said, with the concert tickets, I've got 3 tickets that I can't use, and I'm going to randomly pick 3 people to get the tickets. The order in which I select them makes no difference because the same 3 people will get to go to the concert no matter what order I pick them in. So when the order does not matter, the name of each choice is different. Okay, instead of permutations, they're known as combinations. So these are combinations. The order does not matter, which means that there'll be fewer choices than there would be with permutations. So the formula is going to be different too. Let me show you a quick example. All right, here's one. Let's just say that we've decided to paint a house. There's 4 colors that we want to choose from, and we're going to pick 2 of them. So the order in which I pick the colors doesn't really affect the way I'm going to paint the house. So each choice is a combination. So the question is, how many different choices do I have? So I've written them all down here. And you can see on the left, we've got 6 combinations. But I also wanted to point out that if you notice, I didn't separately list green and white with white and green, because since the order is irrelevant, these are basically the same choice. So if you're looking at permutations, you have 12. But if you're looking at combinations, you have 6. So the question is, how do I do this with a formula? I don't want to write this out every time. So the formula for combinations is a little different. This is what we use for combinations. And if you can see down at the bottom, what we've done differently is we've introduced this new term R factorial into the permutation formula to become combinations. So when we are picking 2 colors out of 4, N is 4 and R is 2. So if you plug in all those numbers, you'll eventually see that you have 6 choices, which is exactly what we proved by just writing them all out. So already we've covered 3 very important concepts: the concept of arrangements, combinations, and permutations. So all 3 of those refer to something a little different. And in each case, though, that factorial operator is hugely helpful in coming up with the numbers that we need. So now, unfortunately, your phone does not have formulas for permutations and combinations, but if you have a more advanced calculator like the TI-84, it will be there somewhere. And in fact, next time in class, we can go over that if you want. If you have a more advanced calculator, I can show you how to do these same things with a formula. So then, okay, so what's coming up next is we're introducing probability theory, which is a completely different topic. So I think this is a logical stopping point right here. We might as well pick this up next time. So don't forget that next time we want to cover the chapter 5 problem set and the sample midterm, number 2. so that we can be ready for the midterm, which would have to be the following week, given that we don't have a class just before Thanksgiving. Okay, so we're getting a little low on time. So next week, we'll do the chapter 5 problem set, sample midterm number 2, and then we'll carry on with chapter 11. All right, so next time I expect to be there in person. I should be better by then, that's for sure. And I'll see you all next time. And by the way, don't forget, I'm going to post the recording as soon as it's ready, besides all these notes. All right, you're welcome. I'll see you all next time. You're welcome. Oh, thank you. I will.